Hello students, welcome to the series of lectures on digital speech processing. So in this video, you'll be able to learn the classroom discussion topic on complex system of a speech and homomorphic vocoder. This is an application, so that we are going to be seeing in this video. So let's get started. So this is the lecture learning outcome. On completion of this lecture, you'll be able to analyze the complex system of a speech and then homomorphic vocoder as an application. So this we already know what is the difficulty when you want to process any kind of the speech analysis, that to estimate the parameter, that is a very biggest task for us, and this problem we are calling as a deconvolution. That is the reason we have introduced the homomorphic system for the convolution. Now when it comes to the homomorphic analysis of a speech model, so this is a complete model of a speech analysis, okay, and this kind of block schematic that we have already know. Now when it comes to this block diagram, we clearly know that from the impulse train generator, we are able to see the sequences of impulse pulses like this. Okay, if the speech signal is a voice, then there could be an impulse. If there is no voice, there could be an unvoiced signal. So like that, it is a sequence of impulses that is going to be generating from the impulse stream generator, and from that we can also able to find the pitch estimation. Okay, the pitch period also we are able to find with the help of that impulse. Okay, and next is the glottal pulse model, and the way how we are going to be speaking, the air is flowing from the lungs and it will travels through the glottal pulse, and then that will be come out of the mouth. So that way we have already know, and here there is a gain factor we are multiplying. Okay, so this complete flow is nothing but the voice, and below this is nothing but the random noise generator block is there, and there we are able to see the some random noise. It could be the white Gaussian noise, or it could be some of the background noise, if at all any speech that is coming from the environmental noise, okay, or the road noise or whatever. So random noise generator, and it is also multiplied with a amplitude gain like this, and then this is the sequence of the unvoiced. This is the sequence for the unvoiced, this is the sequence for the voice, the flow. Okay, now so this vocal tract model is very important. Okay, so the way how we are going to be speaking words, okay, that could be depends upon the parameters of the vocal tract. Okay, so that we need to estimate actually. So in order to find what is the each and every parameter that are associated with the corresponding speech signal, and first we need to understand how the vocal tract has been shaped. Okay, so from this vocal tract parameters we are going to be estimating, and then there is a radiation model. Okay, so this is the complete block schematic for production of a speech. So for voice or speech, we can easily see that the mathematical expression P of n is convolved with the HV of n, where P of n is nothing but the impulse train generated in the time domain, and HV of n nothing but the vocal tract model, is the system HV of n, the system function, and that can be multiplied with the gain. Okay, and for unvoiced, this is the way how we are going to be analyzing U of n, that is coming from the random noise generator, and which is convolved with the again the system function. Okay. Alright, so the same thing, the transfer function for the voice speech separately we have written in the expressions, and this transfer function for the unvoiced speech also we can mention in this slide. Now when it comes to the pictorial representation for the speech signal, and whatever the speech signal that you are seeing here in the left hand side of the slide, is that this is the windowed speech signal. Okay, so the complete duration of the speech I am not able to identify that. I'm not going to be calculating each and every parameter. Before that, what we are doing is that we are going to be taking the frames, frame 1, frame 2, frame 3 like that, and we are applying some windows. Okay, if you apply the window technique to that signal, and then it is very easy for us to compute the parameters of a corresponding signal. Okay, so this is a windowed speech signal for the time samples of 150 samples we have taken from 0. And then this is the log magnitude of the DFT. When you apply the discrete Fourier transform on the left hand side of the figure, and you'll be able to see the spectrum. So this is the spectrum how we are going to be analyzing for a particular speech signal when you record. Now, so from that we can also estimate what is the complex system, because Once we know the Fourier transform of the window speech signal, and it is easy for us to compute what is a complex substrum and what is a real substrum. There is a relation between these two also, we clearly seen in the previous video also. Okay, so there is a complex substrum representation, and this is the substrum representation. Now, so what is the relation between the substrum and the complex substrum that we clearly seen in the previous video also. So always remember, the substrum C of n is a real part of complex substrum, that is x cap of n. So C of n is equals to x cap of n plus x cap of minus n whole divided by 2. So that is the relation between the real substrum and the complex substrum, the way that you are seeing now. Okay, so the substrum is the even part of the complex substrum. This is a very important relation to understand. Now, so this also we clearly seen the complex substrum of the speech, So before we understand how the complex substrum of the speech can be modeled, so first we need to understand the transfer function of the vocal tract. That is very important for us to understand. Okay, so this is the way how we need to represent in the all pole zero method or zero model. So all pole zero model. So when you consider there is a transfer function of the vocal tract V of Z in the Z domain. So for voice speech, only poles, that is AK equal to BK equal to 0 for all the values of K when you consider. And for unvoiced speech and nasals, so this is the signal how we are going to be looking at. Okay, so this is the way how we are representing mathematically when it comes to the complex substrum of a speech. So the same thing, whatever that we have already seen in the previous slide, there's a combination of the vocal tract, glottal pulse, and the radiation will be the non-minimum phase. There is a complex substrum exists for all the values of the n. Okay. Now, which is the simplified the speech model. When you take the short-term speech model, this is the way. When you apply, when it comes to the short-term speech model, the complete speech signal you are applying as a window. Then you'll be getting the short-term speech signal. And similar to that, we can also write the mathematical expression for the short-term complex substrum. It is not that much difficulty for us, because when you apply the window technique, the way how we are going to be looking for the calculation for the parameters, it is very easy for us to compute the estimation. Okay, when it comes to the speech analysis. Now, when it comes to the Z transform substrum analysis, one thing that we need to remember, there's a one important Taylor expansion that we need to apply if at all any problem that you want to compute. So we can then evaluate the remaining terms, use the power series expansion for the logarithmic terms, and taking the inverse transform to give a complex system, which will gives you like this. This is the analysis actually we need to understand. Okay, what happens when you take n equal to 0 for all the values of n that we are going to be analyzing the substrum. So x cap of n is nothing but the substrum, right? So for the substrum parameters, in order to evaluate those parameters, this is the way how we are going to be analyzing. Okay, so doing this, there is a large powers are also there, and how we are going to be overcome those with the help of this formula that you can see from the slide in the rectangle box with yellow background, that is log of 1 minus z equal to minus summation n starts from 1 to infinite z power n by n when mod z is less than 1. So these are some of the examples. Okay, so we need to apply the same formula whatever we have this before seen when it comes to any kind of the signals. In the signal, I have mentioned the example 1x1 of n equal to a power n into u of n, and we already know if you want to transform that into the z domain. So this is a z domain. When you apply the z transform, you will be getting the formula. And when you want to estimate the parameters, and there is a formula that can be useful for us. That is minus logarithmic of 1 minus a within minus. That should be same as like log of 1 plus x or 1 minus x. Okay. And similarly, when you take the example 2, here we have taken the single zero that is outside the unit circle, and then we need to compute the substrum. Okay, so this is the way how we are going to be computing the substrum for each and every example that you consider. And this example is a convolution of the sequences of the previous examples 1 and 3. When you convolve the two sequences, how what is the procedure to compute the substrum analysis. And this is a convolution of the three sequences. Right, now when it comes to the application homomorphic vocoder for the speech, As you already know, vocoder is nothing but voice coders. Okay, there are so many vocoders which are available, but homomorphic vocoder is the best for the speech because it is producing the high speech quality. Okay, that is the reason we are going to be looking for the homomorphic vocoder for the speech, and we also know the benefit for using homomorphic system, because in order to separate the components, okay, separating the component nothing but one is a desired component and other one is undesired component, because it is very challenging task for us to separate the components. Okay, because we need to estimate the parameters, right? Before we estimate, first we need to identify what is the undesired components. So once you identify undesired components, our job is very easy, because we are not in a position to calculating so those parameters, because that signal is an undesired signal. We are not interested towards that signal. We are only taken into consideration for the desired, and those parameters we are estimating. That is the greatest advantage that we are taken into consideration when it comes to homomorphic system. Alright, so what is the procedure for computing homomorphic vocoder to understand? So first we need to complete the system every 10 to 20 milliseconds, and we need to estimate the pitch period, and we need to quantize and then encoding the low time substral values, and at synthesizer we need to get approximation to the system function, whether it is voice or non-voice. Both the things we are going to be looking for an approximations, and then we need to convolve that. So this is the procedure actually we need to understand. So this is the complete picture, synthesizer and then analyzer. So in the analyzer part, first we are going to be taking the speech, and then we are applying window, and you apply DFT, the spectrum will come. When you apply log magnitude spectrum, and there will be getting the logarithmic of the spectrum, and when you apply the inverse discrete Fourier transform, here we will be having the spectrum. And again the spectrum, what is the procedure? We have taken the spectral window. This is a spectrum window L of n. Okay, and we select the low time values, and is of the length of 26 samples, and when you multiply that with the spectrum coefficients, and they will be having the output. This output of this multiplier will be given to the quantizer, and their h cap of n will be evaluated. And from this directly we can easily evaluate the how much of pitch duration that can be there. There is nothing but the parameters which are referred to the excitation. So next figure B, which is the synthesizer. So h cap of n, whatever that we have taken from the quantizer, the same thing we have taken here. And when you apply the DFT, exponential IDFT, and then discrete convolution, we will be getting the synthetic speech. This is as much as very easy for us to compute, the spectrum, and also when you apply the spectral window, then you will be having the short time spectral analysis. So these are the homomorphic vocoder impulse responses. Okay, zero phase impulse response, it is occupying the complete duration of the pulse sequences, left side and the right side of the zero. And when it comes to the minimum phase of the impulse response, we are able to see only the right side of the zero. And when it comes to the maximum phase or the non-minimum phase, we will be able to see the pictorial representation that can be, or the signal that can be available only the left side of the zero. Now this is the summary, the homomorphic system for convolution we have taken, the procedure, everything that we have already know, the complex system that we know, the system real part, and the system for minimum phase signal, the way how that we have already seen in the previous example. This is also the same thing. So this is a short time homomorphic analysis. We need to apply the window technique, that's all, and everything is same. Thank you students. Thank you for watching this.